Uh, so welcome, folks. I was just mentioning that Mike and I were looking at some semantic issues over the weekend. Um, so I just wanted to kind of give some background to that. The basic theorem is that at least with respect to processes in the pi calculus and um, Hennessy-Milner logics, the theorem is that processes are bisimilar if they satisfy exactly the same set of formulae. Um, so now the one interesting question is, what's the notion of bisimilarity or bisimulation in operation? And we can begin to see some of that in the evolution from Hennessy-Milner logics to spatial logics. So spatial logics can see into the structure of programs, and as a result, they can see things that the Hennessy-Milner logics can't see. In particular, they can see when a process is multi-threaded, right? So it actually uses the power operator. And that's not something that the Hennessy-Milner logics can see. So, so you lose the theorem in the shape that it's originally proposed. So spatial logics see more than bisimulation. However, what Kairos and his collaborators showed was that if you put back in all of the transitions that are associated with PAR, its commutativity and its associativity. So if you treat those as if they were actions, then you recover this correspondence between the spatial logic formula and bisimulation. So you essentially have to view the moving around of processes in a PAR expression as actions. And as long as you have some way to observe those, then you recover the notion of bisimulation. And so what that says is, what's the notion of observation that on which you build your bisimulation? Well, this is also foreshadowed when Milner proposed the reduction semantics for the pi calculus. So originally he did a labeled transition semantics. So the very first pi calculus paper with Milner, Perrow, and Walker was a labeled transition semantics. And you can think of it as effectively open world versus closed world. So the labeled transitions are open world in the sense that you don't know the program environment that's causing a particular transition. You only have a little bit of information about what it might look like. Whereas with the reduction semantics, it's closed world. So you know exactly what pairs are interacting to cause a reduction. Now the thing with the interaction, the reduction semantics is that you don't have a good notion of observation. And so that's why Robin and Davide Sangiorgi invented the barbed bisimulation. So the barb reintroduces the observations that are associated with the reductions. Unfortunately, they're sort of loosely connected. So you know that there was a communication, and you know that any observation, any barb that you could assert of P is also assertable of Q and vice versa, but you don't know which reduction corresponds to which barb, at least not in the formal definition. You sort of can infer it, but the barb bisimulation doesn't connect the two very tightly. So let me just stop there. It's a lot of information, but see if any of this is making sense, if it's landing.
So I have a question from the beginning. You mentioned that with Hennessy-Miller logics, we don't have information about reduction. Excuse me. And you said
No, I said we don't have information about the structure, that we don't know about par. You
so do
can't.
you mean, yeah, my question is, you are saying only par, but you really mean any reduction, right? Maybe if we have
No. So Hennessy Miller logics can observe. So for example, if you use barbed by simulation, you still get the correspondence between Hennessy Miller logics and by simulation. So you'll still get a correspondence theorem. It's typically not expressed that way, but you can still push through a correspondence theorem. So they can sense the possibility of reductions. What they can't sense is whether or not those reductions came from a sum or they came from a par.
Oh, I see. I see. Okay. Okay. Yeah, that's clear. Yeah.
So it's essentially, from the Hennessy-Miller logic's point of view, you have a theorem that every par is basically just the sum of all the interleavings. So Hennessy-Miller logics don't see true concurrency.
Okay. Okay. This makes sense.
Right. They only see interleaving.
Thanks.
Sure. It's a good question. If you the spatial logics can actually see the thread structure. They can see the actual par structure. So that's a big difference. And then you can recover this observation if you can recover this correlation between the two if you put in the the actions that are associated with the par, the commutation of P with Q and the associativity of P1 with P2 and P3. So those are the that recovers that relation. But in general, we have this open question of what is the notion of observation that we use for the bi-simulation that we want, and and more importantly, we want the bi-simulation to be congruent, so we can do algebra in the sense that if we know that we put if we know that P in some context C is bisimilar to Q in some context C, same context. We'd like to be able to cancel the context and infer the equivalence of P and Q, right? So that's where this congruence idea comes from. You want to be able to reason equationally, which essentially means being able to cancel, right? So for example, if I have P in parallel with R is bisimilar to Q in parallel with R, I want to cancel the R and get that P is bisimilar to Q. That's the idea, right? It's just like doing arithmetic, right? I've got P times R is equal to Q times R. I cancel the R on both sides and I get that P is equal to Q, right? So this is standard algebraic reasoning. And we want to be able to use that algebraic reasoning with bisimulation. That's the impetus for demanding congruence. Does that make sense to folks?
Yes.
Yeah, no follow.
Cool. All right. What happened between the time that Robin, first published um, the original PyCalculus paper, and then published the functions as processes paper, which gave the reduction semantics, was that people started coming up with this sort of cottage industry of different notions of bisimulation to sort of capture their favorite semantics for processes. And as I said before, there's some pretty powerful results that show that all the known notions of process equivalence, are some form of bisimulation plus a filtering. So bisimulation is somehow very, very fundamental. Every notion of equivalence factors through bisimulation effectively. So that's really important, right? It says that bisimulation is somehow the right notion. And so if we can figure out, how to get the observations right, then we can get a bisimulation that corresponds naturally to the reduction semantics. And that was work that Peter Sewell initiated and Milner and Leifer picked up on. So Peter reflected that it was sort of folklore that you could use contexts to label transitions. But the issue was that there you might have the action site of a reduction in a particular context. You could make an infinite number of variations of that context, right? Elaborating other parts of the context that ad infinitum, but leaving the action side alone. So the question is which, so you get a lot of labels for the same reduction, and the question is what, how do we think about those labels? Now, on the other hand, having an algebra on the labels is a really good thing. That's a very important thing. And so obviously, if they are context, then you do inherit an algebra on the labels. So the way it's been characterized is sort of finding the smallest context, largest whole. A recent paper by Sobczynski, Sassoni, and Klin, they refine some of the work that Milner and Leifer and Sewell did to sort of carefully capture some of these ideas. And Mike and I have been talking about this work, and the reason we're thinking about it is, of course, we would like to relate the discrimination of the type system that we provide with the discrimination of some bisimulation. Right, so that would be an ideal theorem to have in the Ladle paper. And so you use category theory because category theory gives you a way through universal properties to talk about sort of smallest, smallest context. But what Mike realized this weekend is that it's not smallest, it's prime. What you want is that your context can't be factored through some component context where the action site is wholly housed in one of those components. Does that make sense? Are people following along?
So when you say the smallest context, does it make sense to think about context as also something that has reductions or normalization, so that we can say, oh, I can reduce this context to some normal form and I can compare to other, and Does this make sense?
I think the important thing is to think of context as having a hole in it, right? And wherever you plug the hole, that should, if it's going to label a reduction, that hole should provide an interaction site. So, for example, a context which is, whole par send, some value on X. Um, Well, obviously, if you plug, wait on X for something and then do something into that hole, that's an interaction site, right? Now, notice that you could also elaborate that context, right? So you could say it's send the value on X in par with, wait for something on Y, in par with, wait for something on V, and so on and so forth, right? So I could get lots and lots of contexts, all of which have an interaction site at X, right? Because it's send something, some value on X. There's a hole in par with send something on X in par with yada yada yada, right? So I can get an infinite number of contexts, all of which interact at X. Sort of what we'd like to do is to say, well, if I can factor that context into, some components, and that in which I've got, the interaction site localized to one of those components, right? Then that context is not somehow the best label. So what we're really looking for is kind of primes. Does that make sense?
Yeah, but I still don't see how. Yeah, maybe I should wait a little. Yeah.
Okay, all right. So there's some fairly rich category theory that has to do with doing push outs over slice categories that I'm not going to introduce here now. Um, but essentially that characterizes some of what we're interested in. However, the issue is that for us, we don't just have pars. Um, we have some K constructor, right? So we're suggesting that the rewrite system be interactive, but we don't know that it's commutative, for example. Like in the case of SKI, it's not commutative. So what that uh, suggests is that we need to look at not just factors, not just one kind of factor. We have to look at left and right factors. So that was the observation that Mike had this weekend. That's a very, very lovely observation because it helps us to take a step towards being able to characterize the type, the granularity of program semantics that are picked out by the types versus the granularity of a derived notion of bisimulation. So in particular, Miller and Leifer and have been able to derive bisimulations, derive a label set such that the corresponding bisimulation is a congruence with respect to the rewrite system. So that's, now the thing is that it's a little bit tricky, it's a little bit subtle, and so the results are not as widely applicable as we'd like them to be. The SSK paper, Sobczynski and Sassoni and Klin, that paper expands those results. But again, it needs more work, and they acknowledge that it needs more work. we're looking at that work as inspiration, but we'd like to, we'd like to, we have only one goal, right? Which is to get a biosimulation that has the right relationship to the type system. Now, of course, you could go the other way, right? If they're able to nail down that work, then you could probably derive the type system from the labeling system. That would be another way to go, especially if the labels have an algebra-like context. So that would be another way to go. But essentially, that's sort of the work that we've been pursuing, is just trying to make sure that we can say crisply, exactly what distinguishing power the type system has, and then of course immediately on the heels of that, we'd like to look at complexity, right? So that we can say, for which fragments of the type systems and fragments of the language, the type checking is decidable, right? So that's another piece of the puzzle. But this is all ongoing research. Does that make sense? Are people sort of following along with what I'm saying?
I'm following, not completely, and it's not completely clear for me, but you mentioned biosimulation with filtering. Is this related, what you just said about types decidability?
Yes, that's exactly right. That's precisely it. So you'd get a so if you leave the language alone, so you leave the programs alone, then if it's exactly equivalent to biosimulation, it can't be decidable, right? So if you're going to leave the language alone, then whatever you're doing with your formula or types has to be less expressive than biosimulation, or there will be things that you could express with your formula that simply can't be decidable. So they have to be more permissive. They have to be, less distinguishing in order to get some decidability. But remember, you got two sides of this thing that you can muck with. So in the Kyrase paper, what he does is, rather than muck with the formula, he looks at a particular class of a fragment of the pi calculus, and shows that for that fragment the type system is decidable. So and it turns out to be, the programs are interesting. I mean, in general, right, you're always going to come up against the halting problem. So you're constantly in this balancing act between, how much can the types see, how much can the programs express, so that you can get, like, if you need full expressiveness in the programs, you have to dial down your types. If you can limit your programs to something, you can keep the expressiveness of the types, or you can kind of, split the difference between the two. But that's kind of the balancing act you're constantly mucking around with, in order to get type checking for an interesting enough class of programs. That's basically the idea. Does that make sense?
Yes, thanks.
Sure. One quick side note. No one seems to have pursued this, but I think it's actually quite interesting. With Yoshida's work on combinators, she gives a complete breakdown. She says, look, we can express the pi calculus in terms of these small set of atoms, so we can consider the different fragments where we have the presence or absence of particular subsets of those combinators, and then she gives a characterization of each of those fragments, right? Their expressive power with respect to those. So you could imagine that if you have contexts as your observation labels, then you can, again, you can use this minimality, these separation results to say, well, we're only allowed to use contexts that have, these atoms and not these others, these combinators and not these others, and get expressiveness results that way, both in terms of typing and in terms of fragments of the language. And so that seems to me a very interesting way of sort of saying where the notches on the dial are. You can dial the expressiveness, but you don't know exactly what the notches on the dial are, but Yoshida's combinators give you those notches in some sense. So that is another area where we'd like to kind of expand the results a little bit. Anyway, so that's kind of the work to date. Any questions, comments, thoughts?
Greg, I was wondering, is any of this tied to the semantic web technologies at some level? I mean, they seem to be somewhat a lot more loosey-goosey than having a lot of mathematical rigor, but I was wondering if there's probably work.
So it's an interesting question. So my argument has always been that what is put forward as semantics in the semantic web is not semantics at all. And the reason is because you can always change your data structure. So essentially what they're doing is asking questions about the shape of data structures. That comes down to what you can see. And so we kind of have a really clear understanding of what that means in terms of semantics, right? So in particular, you can look at functions and you can say, well, the type of the function that takes a list of natural numbers and produces a list of natural numbers, right? So that's a fairly rich data structure, data type, but both sort and shuffle, which do opposite things to lists of natural numbers, will match that type. So it's not a particularly discriminating sort of thing to look at. But also because you can always refactor lots of data structures, right? So we can implement sets in terms of lists. We can implement lists in terms of sets. Seeing these, like when do we have essential differences in these different factorizations of data structures? Essential in the sense of relevant to some domain, we don't know, and it's not something that we can draw upon from the kinds of questions that you can ask of data structures. It would require data structures plus adding some semantics, which means that you didn't derive the semantics, you added it in, and it's being done by humans. So that's not particularly semantic at that point. However, if you are, I would argue that the moment you have something like the Hennessy-Milner logics, you're starting to see real semantics. So that's the point at which you could actually build a semantic web, because you're being able to ask questions about behavior and not just structure. And the relationship between behavior and structure nails things down much more profoundly. So it does give you a semantic web. And in particular, what I argued in that note that I put out a few weeks ago is that if you have, we can observe that types classify programs. We can also observe independently that some programs are simulations of things in the world, right? So flight simulators are simulations of aviation. Some programs are simulations of protein folding, right? And we can go on and on and on. So since types classify all programs, and some programs are simulations, types classify simulations. And if those two arrows of classification are relatively faithful, then you can get relatively faithful characterization via types of things in the world. Does that make sense?
Yeah. I mean, you and I talked about topological formation for requirements gathering, topological functioning models. And then you kind of steered me towards bigraphs as a more dynamic or more complete model. So I was thinking if you were to do those for business requirements, perhaps starting with topological functioning models because they're simple to do, and then where you need add the bigraph type of a model, then you should be able to derive the types from there sort of automatically or semi-automatically, correct?
I'd have to look at more of the details of your proposal. I mean, first of all, I don't know enough about the topological functioning models to really say. I mean, in general, you have to understand that topology and computing are really funny, right? In the sense that the topologies that match with compute don't observe any of the standard separation properties, right? So like all of our intuitions from topology, at least if you're like me and you studied topology as an undergrad or a high school student, then you built up all these intuitions around the separation properties, right? Like, can I separate a point from an open set? Can I separate 2 points via 2 open sets, right? So T0, T1, T2, T2 is Hausdorff, all of those kinds of things, right? So none of those, the topologies like the Scott topology, which are typically associated with modeling continuity of computable functions, they don't have those separation properties. So all of the things that we think about in terms of topology, they're really wonky in the computing world. So the connection between topology and computing is very different than our standard, sort of intuitions about topology, like, using a genus to classify spaces and things like that. All of that stuff, homotopy theory, it doesn't move over as directly or as as intuitively as we might think in computing. So that's why I'm just saying I really don't know enough about their approach to be able to give good advice. But I would be very skeptical of if they're putting forward topology as a simple and intuitive way to capture a computing phenomena, well, that flies in the face of everything we know since the 1960s about the connection between topology and computing.
Interesting.
Yeah.
Looking at the Rosetta Stone paper here, they relate manifold to a data type and a abordism to a program.
That's right. That's exactly right. But if you want to see it in action, just go look at Dana Scott's original work, right? I mean, the thing that made lambda calculus so suspicious was that everyone could see that the lambda calculus was whatever your semantic domain was for lambda calculus, call it D, then it had to be the case that D is isomorphic to D arrow D, right? So the domain is isomorphic to the function space of the domain to itself. But we know that function space grows like crazy, right? If you consider omega to 2 to the omega, right? So that's a jump from countable to uncountable, right? So it grows like crazy. So how could the domain be equivalent to its own function space, right? That's what made lambda calculus so suspect, right? People thought eventually they were going to find some inconsistency in lambda calculus because of this phenomena. And it was Scott who said, well, actually, you don't consider all the functions in the function space. You only consider the continuous ones, and you line up the notion of continuity with the notion of computability, right? So the Scott topology is, a notion of topology that lines up computability with continuity. So that's that, and that led to all, Scott domains and, the Lawson topology, all that stuff. But so I would heartily recommend taking a look at that and then comparing that to the topological functional models. But if they're trying to capture not a notion of topology, but a notion of location, right, then that's different, right? If they're sort of abusing the word topology and are really trying to capture a notion of location, then the bigraphs captures that idea pretty well, or at least it's a workable. I mean, you can calculate with bigraphs, and you have notions of places, right? You might want to consider, something even simpler, like just the ambient calculi, right, which has a tree of regions. And what does it mean to go into a region, go out of a region, or dissolve a region, right? And that's a very powerful notion. It's a different line of research. It gives rise to the brain calculi that Luca found, right? So that's also very interesting. So that might be another way, but deriving types is tricky, precisely for these computability reasons I mentioned before. Interesting questions, though. I'm going to jump off. I need to get ready for the dev stand-up. So I will catch you guys next week. Thank you so much for all the interest and the hard work, and I'll see some of you in dev stand-up in about 20 minutes.
Thanks.
Yeah, thanks, Greg.
Thank you.